We've seen a lot about how to solve single differential equations. I want to talk now about systems of differential equations, and we're going to talk about linear equations first. I want to motivate this with an example where you can see how a system is truly necessary to solve some physical problems. A spring that's attached to another spring. The two masses at the ends of the spring, if you pulled on them, they'd be independent, right? You can move M1 kind of all over the place, you can move M2 all over the place. When you let go and you're not moving it anymore, then they're no longer independent of each other, right? The bouncier the first spring is, that might affect the second spring and the position of M2, etc. So to do this, let's call the position of M1 x. So x equals 0 will be the equilibrium position of the first spring. And we'll call the position of the end of the second spring y, so that y equals 0 is the equilibrium position of the second spring. What does Hooke's law say in this situation? On the left-hand side, if we just think about what x does, we have the ordinary left-hand side for Hooke's law, right? Some multiple of m1 times the acceleration plus k1x, that's the force from spring 1, should equal the right-hand side. But what's the right-hand side? Well, the thing pulling on spring 1, the thing imparting additional acceleration to spring 1, is the mass at the end of spring 2. What is the force imparted from spring 2? Well, it'll be k2, that's the spring constant for the second spring, times the difference in the two current positions. So that's an equation involving x. You can see the equation involving x necessarily involves y. Let's write down the equation for y. You should think of the second spring as sort of basically acting independently. The only difference is that if the first spring is extended really far, then the equilibrium position for the second spring has to change. And so instead of getting the normal equation from Hooke's law, you get k2 times y minus x. So that is a system of differential equations. Now I'm going to clean that up just a little bit. So it's not a problem, you might think, to solve equation 2. You could maybe write down the solution of the corresponding homogeneous problem, where that right-hand side was 0, try to write out the undetermined coefficients problem, figure out what you're looking for. The problem with that is that that right-hand side is k2 of x, right? So in order to solve the undetermined coefficients, you have to already know what x is, but x is unknown here. Okay, so once we know x, we'd be done. So let's go in at the equation for x, equation 1, and see if we can solve it. Again, there's no problem to attempt to use undetermined coefficients, but then the right-hand side is k2y, and we don't know what y is either. So in order to find x, we need to know y. In order to find y, we need to know x. We're just going to keep going around in a circle and never get anywhere. The term for this is coupled. We say that the system is coupled when the coefficients, or the right-hand side, of one equation depends on solving the other equation. So if we're going to solve this, we can't just solve x first and then try to solve for y. We have to solve them at the same time. Okay, this is a second order system. You can see it's got some second derivatives. We're going to focus first actually on the first order systems. Why would we do that? The reason we're just going to focus on first order systems is that it turns out you can really turn any system of equations into a first order system. Let's do that in this example. The first thing I'm going to do is go ahead and clean it up so I get the ones in front. And then I'm just going to arbitrarily decide to introduce some new variables. Those new variables will be the derivative of x and the derivative of y. What I can do is take those definitions and think of them as equations. So what I want you to do is realize that this is a system of differential equations. Let's rewrite it a little bit. The only terms that I've changed are these two terms. And notice if u is dx dt, then du dt is just the second derivative of x. So by doing a trick like this, we can get rid of second order derivatives as needed, third order derivatives, fourth order derivatives. We can keep doing this until we've taken our system, and by introducing new variables, all right, so it wasn't for free, we had to introduce new variables. Now I've got a system with 4 variables, whereas before I had only 2. By doing this, we can build a first order system. So our plan of attack in learning how to solve the systems of linear differential equations is going to look like this. What we want to do is build a machine that takes in a system of any order and spits out solutions. So the first step we've actually already done. This is called reducing the order. So to reduce the order, you have to increase the number of variables, but other than that, it's pretty easy to do. The output of that is going to be a first order system, possibly with many, many variables. What we're going to do is feed that into our device for solving first order systems of differential equations, or FOSDEs as I'll call them. We're going to develop that in the next few videos. So in the rest of this week, we're going to be developing exactly what goes in that box. Right now, we don't know what goes in that box. But what comes out of that box are solutions to this first order system of differential equations. So the question is, how do we relate those solutions to the solutions of the original system we had? And let's look at this example to see. So if we actually solve the system of 4 differential equations, the first one, when we solve it, it should give us a solution which we might call u of t. The second one will give us a solution x of t. The third one will give us v of t. And the fourth one will give us y of t. So once I've solved that, what do I have to do? Just forget about u and v, right? They were something I introduced to solve the problem. They're not what I'm looking for. So all we have to do is forget those variables. If I know all 4 of them, then I know x and y, which are the 2 that I was interested in, and I'm done. So that's what we're going to do. Our job in the rest of this chapter is figuring out what goes inside that box. How do we solve first order systems?